Good morning, good afternoon, and good evening to everybody. Today we welcome you from our EMAG location in Farmington Hills, Michigan, from where we support our customers in North America and beyond. In former years, we would be now all together enjoying each other's company, and let's hope these times will come back soon. There's a light at the end of the tunnel. But in the meantime, I believe we have all learned and perhaps started to like the virtual way of how we communicate and share information. However, this also is not possible without a lot of effort in planning and organization. So I don't want to forget to say thank you to the VDW to make this webinar a reality today. Before we start, I would like to give a brief introduction. To my left, we have Mike Rose, Sales Director of EMAG LLC. He will guide us to the first part of our presentation. Myself, Johan Arnold, President of our operations in the US, I will cover the second part of it before we open it up for the Q&A. Mike, please take us from here.
Thank you, Jochen. Well, we have to start somewhere, so we'll start with a little bit of history here. So as far back as 1881, there was a tricycle on the streets of Paris with a power source being tested. 30 years later, both Thomas Edison and Henry Ford had produced automobiles that had a 50 to 100 mile range. By 1920, major metropolitan cities had up to 50% of their automobiles that were electrified. Only during the gasoline and availability of large amounts of gasoline over time in the electrified start push button of the internal combustion engine did e-drive become a niche product. Moving into the 21st century, with increasing environmental regulation over the last decade, this has forced major automotive OEMs to develop serial e-drive production systems. Now we'll move on to the rotor shaft processing, and then obviously return to Jochen for the assembly portion of the presentation. Within this slide, we show the typical powertrain components inclusive of a ICE. You have your engine, your valve train, transmission, and your exhaust system. This is what the powertrain components of tomorrow looks like with an electrical vehicle. As we push towards EV, we move towards propulsion systems. And today we will focus on the machining and assembling of the rotor, a key component to the e-drive system. What you'll notice here, all of the labeled components within this slide are considered to be strategic components within the EMAG group. Thus, EMAG focuses and has focused on developing multi-technology solutions that can be connected for both the machining and assembly of these components. You'll see in the upper left-hand corner that your standard ICE engine operates between 800 and 7,000 RPM, while these new electrical vehicle gearboxes reach peak torque at 0 RPM and have the capacity to reach speeds in excess of 20,000 RPM, creating the demand for more precise components and assemblies. Displayed on this slide is the cross-section of a rotor assembly from an induction motor, often found within today's electrical vehicles. The assembly consists of the rotor shaft, the lamination stack, which is held together by a high-pressure die-casted aluminum cage. This slide presents the turning process for the rotor shaft, starting with op 10 all the way through op 80. The preceding slides will present the process chain in greater detail, but please take note of operation 30, which is a third-party content for ID spline machining, along with op 70, which is assembly of a freeze plug and collar, subsequently machined in operation 80. What you'll see here is operation 5, operation 10, 20, and then operation 23. In the lower left window, you'll feature our VTC 200 4-axis vertical turning center fed by a raw parts conveyor and automated by EMAG's own track motion system, which is a 4-axis system similar to a robot on a rail. This provides part handling to the turning machines along with subsequent downstream processes such as the blow-off device and the post-process measuring device. Moving on to Op 26 through Op 40, you'll see again, for Op 26, we incorporated a third-party technology from one of our systems partners for the toothing or ID spline. And then you'll see the part is then induction hardened with our own LDEC Mind L1000 rotary table induction hardening system. Again, this cell comes with 2 robots and a blow-off station for the subsequent downstream processing. Moving on to Op 50 and Op 60. For the production requirements for these operations, you'll see that we doubled up on both Op 50 and Op 60. Operation 50 is utilizing a center drive work holding solution, allowing simultaneous ID turning of opposing sides of the shaft, while Op 60 completes the semi-finished turning of the OD. Again, supported by 2 track motion systems, a gantry, and a blow-off station for subsequent processes. Moving on to Op 63, 65, and 70, you'll see that within this cell, we assemble both the freeze plug and the shoulder to the rotor shaft in preparation for finished turning of the shaft. I'd like to highlight the post-process measuring device, the marking station providing traceability, and the 2 assembly cells. Okay. Lastly, this final video shows the entire cell sequence for part processing, using a simulation software that helps to discover potential bottlenecks in throughput early on in the design phase when we're discussing these solutions in these systems with major OEMs as well as tier 1 suppliers. What you'll see here is technology connected by the EMAG group. And to recap, you'll see that this line includes 7 vertical turning machines, 3 track motion systems, 3 robots, 4 post-process gauges, along with multiple gantry systems for blow-off stations and marking stations, again, for traceability of the components moving through the cell. Now I'd like to hand this over to Jochen, and he will speak in regards to the assembly side of the rotor.
Thank you, Mike. Thanks for enlightening us on the manufacturing process of the rotor shaft. Now we want to direct your attention to the assembly process EMAG Group offers to the rotor lamination stack, the stator lamination stack, and finally the thermal fit of shaft to rotor stack as sub-assembly of the E-module. The slide here shows the individual processes from sheet metal stampings all the way to an assembled rotor stack, which includes the measuring of the height, the parallelism, as well as the marking process. Before then, it is packaged for the next process in the cell. Please. EMAG is using index rotary dial machine as their assembly systems. Here, in particular, you see 2 of these machines identically put together in parallel in order to machine or assemble a stack in 4.3 seconds stack time. Each machine is consisting on a rotary table with 5 positions from where the sheet metal parts or sheet metal is introduced, and then in indexes from one station to the next, all the way up to station number 5, where the robot then picks it up and prepares us for the next downstream operation. This one here shows actually, we now have two parts. We have the assembled rotor stack lamination, and we have the shaft that Mike actually explained to us how we got to this stage. So in order to make this an assembly, it requires that the rotor stack will have to go through a process called high pressure aluminum die cast that takes actually the stack and cages us in. Before it is then reintroduced into the assembly cell, where it is being fit under thermal conditions using our induction technology with the rotor. And then finally, not finally, but one of the next steps are the OD turning of the subassembly before it is then being marked, gauged, balanced, and packed. This shows you an overview of the cell, starting with the supply of lamination stack, which then will actually be introduced to an area where we do, or a partner of ours, perform the high pressure die cast operation. The part then is being reintroduced to our cell, where it is being assembled with the rotor by using our induction, followed by our 2 VTC 204-axis machine, also here connected in parallel to maintain takt time of the cell, where the OD is being machined, followed by a post-process gauge that assure the highest and tightest quality over the shift of a day. Together with our sister tool strategy, we can guarantee the most uptime in this process. We are then following with a dynamic balancing process, gauging, cleaning, and packaging. Now, this next few slides will show you and illustrate actually some videos of the cell to better show you the process in detail, where here the lamination stack is being put onto a conveying system, from where it is then introduced into the aluminum die cast area, before it is then, as a finished part, reintroduced to our cell for the assembly with a shaft. This slide now is showing the OD turning of the subassembly of the electric motor, which is consisting of the rotor lamination stack and the shaft. As a matter of fact, we actually are here still on the assembly side, where we now fit the rotor shaft into the lamination stack.
Twin station.
The twin station, yes, Mike, that's correct. It's a twin station so that we minimize load and unload time as part of the takt time of this machine cell. Power supplies, inductors, and the entire cell comes from the LDIC division within the EMAG group. Now we are having our VTC 204-axis machine, where we pinch turn the OD, followed by the finish cut on the OD, which can be either performed dry or wet. The next video shows, it's not playing here. All right. Yeah. Okay, now it's starting to move. And what you can see here is actually the moving of the parts with those robots is not just for this presentation to show you some movements on slides, but it's also being used to optimize the cell configuration to identify bottlenecks way upfront in the design stage, so that corrective actions can be taken before we actually have to reproduce parts, or have to produce actually the cell on the floor. Some of our rotor shafts are coming as a two-part design, which is no problem for the EMAG group, as we have our division LaserTech that has a machine which is our VLC 160H machine that laser welds produced rotor shafts, being shown better on the next video to come, in two stations, where on one side we are load and unload, while we are in the center welding already the other part, and then it moves over, please. As shafts and in the rotor assembly business have to be sometimes also hardened, as Mike mentioned it before, on the rotor shaft itself, we are using our induction Mind L1000 machine with an index rotary table in order to obtain these tasks. So your benefit deciding for the EMAG product line is obviously we have the experts that you are looking for on staff, and we are one face to the customer, as we also call it, as being one EMAG, to present to you the best possible and most cost-effective solutions for your needs to produce not only rotor shafts or assemblies, but all kinds of other parts that you can turn, weld, harden, or grind, or harp and shape if it comes to gears. As you might know, EMAG is globally operating. Today, as I mentioned, we greeted you from our facility in Farmington Hills, Michigan. And if you are located in Asia, or if you are located in Europe, we certainly have several locations that will be able to take care of your needs. Thank you so much for your attention. And with that, we are opening it up for the Q&A.
I don't see anything.
So far, no questions have been reaching us.
I think one thing I'd like to say, Jochen, and obviously to the audience, is this is not a new segue into connecting technology. EMAG has done for many, many years, provided manufacturing systems of precision metal components, specifically to major automotive OEMs, as well as major tier 1 suppliers. So the segue into electrification in rotor machining assembly just makes complete sense for us based on our experience within powertrain and specifically automotive.
Yeah, that is true. Not sure if you have technical difficulties to receive questions and answers, as we had a bit of a rookie start this morning. But is there a question or answer?
What is the typical takt time for these processes?
Typical takt time, I mean, as multiple as shown here on the slides, takt times were about 5 seconds per process. For for the assembly. So it depends obviously very, on the lot sizes, and then we see this segment to be increasing in importance in our daily life. What started very slow, I think we will actually see an increase in volume, and with that a decrease in the requirement of cycle time, which we obviously have the solutions to scale it up or scale it down as it is needed.
And is machining process optimization an important element to meet their takt time? Well, yeah, of course. Optimizing the process is critical to meeting the takt time. And with EMAG's experience within the automotive industry, typically providing somewhere between 45 jobs per hour on a transmission, we're quite comfortable with optimizing takt times and producing parts every 30 to 45 seconds from the machining standpoint when producing these high volume components.
Another question? I mean, obviously, one thing to be said with one EMAG, we have several divisions within our group, as I mentioned, starting from the laser welding over to the induction hardening to the gear hobbing. But an important division for this is also our systems group. It's located in Saarland, Germany, that have specialized and put their focus on the assembly process, on optimizing actually the cell concept so that we do not have bottlenecks. And if we have bottlenecks, we can scale accordingly so that we have a smooth throughput. And they also bring all the other divisions together so that flawlessly we can execute on a cell that we have seen here within this presentation today. And last not least, training and the support is what is needed to implement such a system throughout the world, not only in Europe, not only in America, but also in Asia. EMAG is equipped with a systems group and its several locations throughout the world to support that effortlessly.
Yeah, another question. If grinding is required, could you integrate? Yes, is a direct answer. We have additional technology similar to what you saw on the VTC series. We have a VTC 100 GT specifically that would handle a rotor shaft, and it has the capacity to both turn and grind in a single clamping. So that machine would be and could fit quite well into this line if the process were to require it. Let's see, additional questions.
No?
No.
All right. So it looks like that there are no more questions that are reaching us right now, either through technical difficulties or perhaps there are no questions to be asked. We certainly hope that our presentation today was informative to you. And if you have any questions, please do not hesitate to reach out. We can be found, as I said earlier in my greetings, good morning, good afternoon, and good evening all over the world. So looking forward to hear from you. Thank you.
Thank you.